Hello, today I'm going to discuss the experimentally discovered fact that matter under some circumstances can disappear and be converted into energy. So the experiment that I'm going to discuss is some mass disappearing and energy appearing as determined by experiment. All right, now it's very obvious and simple that the amount of energy is going to be a constant times the amount of mass. In other words, if you double the mass, you're going to get twice as much energy. So E is equal to K times M. And it's also obvious and a basic elementary physical fact that E has to have the units of energy. And the most natural way to give it the units of energy is to multiply it by the one constant that appears in all of these particle disintegrations, and that is the speed of the radiation emanating from the particle, which is always constant with respect to the particle as its source. So in that case, E is equal to K mc squared. K is a dimensionless constant. But that still leaves us with the question of what is K, and I'm going to try to evaluate that by some elementary considerations. So the model I'm using is a particle of mass m, and after a certain time into the disintegration, m remains and m minus m, this portion here, has been disintegrated. Now, the energy at this instant is the mass energy, is K mc squared, and the kinetic energy at this instant is the kinetic energy of this remainder m E equal 1/2 mv squared. I'm assuming that all the energy, all the mass energy at any instant that's been released goes into accelerating the remainder of the particle of mass m. Now from Em and Ev, we get that Dem is K dmc squared, and the elementary calculus, I'm not going to dwell on that. And that Ev is 1/2 the mv squared plus mv dv. Now, to get a correct relation between the differentials, which gave me the hardest time, that the signs was a nightmare. And finally, the signs that come up physically are the signs that give you a logical result. And so the model for the differential is that I have a mass m and a slice dm, which is lost and converted into energy. So now, in the process of this slice dm being lost and converted to energy, the change in the total energy is 0. So the change in the energy is that this slice contributes energy K dmc squared. At the same time, since it's lost, an amount of energy 1/2 dmv squared is lost, and in addition, there's the momentum term mv dv is increased by the energy that's released from the dissipation of dm. And that's basically it. That takes care of the... After that, it's just elementary. After that, it's just elementary calculus. So I'm not going to go through the details. If you separate the variables and integrate, noting that the integral of v dv of a plus bv squared is 1/2b log v squared plus ab, then you do the integration, and the limits for m is that m goes from being the entire mass to m equals to m, and I'm integrating at an intermediate step where I'm integrating from m to m, and the velocity starts off at 0 and goes to v. Now, if you do this elementary integration, you get log m over m is equal to this term here. Now, just equating the two logs, the m over m and this term here, you get that m times 2kc squared minus v squared, that m times this term is equal to m times that term. Now you have the additional condition from the assumption that the entire mass is consumed and that when it's consumed, at the very last instant, at the very last instant of infinitesimal mass left, the velocity is c squared. So you get, when m equals 0, the velocity is c, which implies 2k c squared minus c squared equals 0, from which you get the result that k is equal to 1/2, and then the energy of m, therefore, is 1/2 mv squared. Now, if you substitute k 1/2 in this expression, you get that m is equal to 1 minus v squared over c squared times m. I wouldn't read too much into that. That's just telling you that intermediately in this almost instantaneous process, when the mass is, when the velocity is a certain value of the remaining mass, the remaining mass is 1 minus v squared over c squared times m. Thank you. Okay.